Okay, for the last topic is the area of a triangle. Okay, so here we'll try to solve for the area of triangle in terms of trigonometric ratios, specifically to the sine. Let's use it with the figures that we used earlier in our oblique triangle. Okay, so here we identify that in figure 1.1, both A and B are acute angles, and figure 1.2, the angle B here is an obtuse angle. Okay, so as we recall, the formula of a triangle is area is equal to 1/2 times the base times its height. Okay, so notice, let's look at the figure 1.1. Okay, let's look at the figure 1.1. And let's identify the sine B. Okay, so sine B here is the opposite, which is H, and then its hypotenuse, which is A. Okay, and if we're going to identify the value of H, that is H is equal to A sine B. Okay, and as you can see here, the base of this triangle is C, right? And the height of this triangle is A sine B. So let's try to substitute it in our formula. So 1/2 times the base, which is C, and then the height, which is A sine B. And as we simplify that, we'll obtain 1/2 AC sine B. Okay, and in the same manner, if we'll explore this figure 1.1, we'll also obtain this, that we have 1/2 AC sine B is equal to 1/2 BC sine A is equal to 1/2 AB sine C. Now, how about for the figure 1.2? In figure 1.2, as you can see here, if we will identify for the sine B here, I will have this A, the height as equal to A sine 180 degrees minus B. Okay, and we identified it earlier. Okay, that 180 degrees minus the angle B is the same as the B, or the angle B. So therefore, the height here is H is equal to A sine B. So substituting it again, we'll have the base of C, and then we have the height of A sine B. So which is also 1/2 AC sine B. So in general, our formula for the area of triangle is 1/2 AB sine theta. Okay, so let's have an example. So find the area of a triangular lot having two sides of lengths 10 centimeters and 3 centimeters and on included angle of 120 degrees. So given that we have here 120 degrees as our angle, and then we have two sides as 3 centimeters and 10 centimeters. So as we substitute it in our formula, we'll have this one. So substitute that. That is 1/2 3 times 3 times 10 times sine 120 degrees. And that is 15 square root of 3 all over 2. Or, in decimal form, we round off it to the nearest hundreds. That is 12.99 square centimeters. Another example. Find the area of a triangular lot having two sides of lengths 90 meters and 52 meters and an included angle of 102 degrees. So we have here again 102 degrees as our angle, and then the sides we have here 52 meters and 90 meters. So as we substitute it in our formula, we'll have 1/2 times 52 times 90 times sine 102 degrees. And if we'll solve that in your calculator, you'll obtain 2,288.87 square meters. Okay, so actually this is, you are familiar with this because of your geometry class. Okay, but we're going to focus in Heron's formula. So I derive and I will use the concept of the area of the triangle that we have earlier. Okay, for this Heron's formula. Okay, so recall again that the area is equal to 1/2 AB sine C. Okay, so if we will square both sides, that is a squared is equal to 1/4 a squared b squared sine squared c. And if you will recall the Pythagorean identity, sine squared c can be expressed as 1 minus cosine squared c. Okay, and 1 minus cosine squared c can be expressed as 1 minus cosine c times the quantity of 1 plus cosine c. Now, let's try to identify the value of 1 minus cosine c and 1 plus cosine c. If you will recall in the cosine law or the law of cosines, we have here cosine c is equal to a squared plus b squared minus c squared all over 2ab. Okay, and if we will add 1 both sides, we'll have 1 plus cosine c is equal to 1 plus a squared plus b squared minus c squared over 2ab. Okay, and then LCD, finding the LCD, which is 2ab, we'll have 2ab plus a squared plus b squared minus the c squared. Okay, so from this, a squared plus 2ab plus b squared, we can express that as a plus b squared. Right? So a plus b squared minus a plus quantity a plus b squared minus c squared all over 2ab. So here, as you can see, we can express this as difference of two squares. So we have here a plus b plus c and a plus b minus c. Okay, so from this difference of two squares, sum and difference of two squares, we have a plus b plus c times the quantity of a plus b minus c all over 2ab. So similarly, actually, if you were explore this, okay, and identify the 1 minus cosine c here, you'll obtain this one. C plus a minus b times the quantity of c minus a plus b all over 2ab. Okay, so you can explore this and you can solve for this one. Okay, so given that we have now the value for 1 minus cosine c and 1 plus cosine c, we have another representation. Let's substitute that. Okay, let's substitute that. So 1/4 a squared b squared times the quantity of c plus a minus b times the quantity of c minus a plus b all over 2ab times the quantity of a plus b plus c times the quantity of a plus b minus c all over 2ab. Okay, so simplifying this, as you can see, we have here a squared and in our denominator we have 2a also, so we can eliminate that. Also with the b squared, we can eliminate that, right? So the remaining factors now here are 1/4 times the quantity of c plus a minus b, c minus a plus b all over 2 times the quantity of a plus b plus c times the quantity of a plus b minus c all over 2. Okay, then we can re-express this. Okay, we can re-express this and separate them. Okay, let's separate them. That c plus a minus b all over 2 times the quantity of c minus a plus b all over 2. Okay, so it's the same. We're going to have the factors of 2 here. Okay, so that is here. And then a plus b plus c and then a plus b minus c. Same with this also. So we'll have this. Okay, so 4 times 2 times 2, that's 16. So 2 times 2 times 2 times 2, that's 16 also. So we just re-express this right-hand side. Now, so from this, okay, let's try to have this expression. Same with the other factors. Okay, so in order to do that, here let's express this as a plus b plus c all over 2 minus b. Okay, so if you will simplify this, If you will simplify this first factor, you will obtain this. Okay, same with this. If you will simplify this, you'll obtain this one. And this one, if you will simplify, you'll obtain here, this factor. Okay, so as you can see here, we have a plus b plus c over 2 as our expression. So we can simplify this. Let's represent that, let's say, as s. Okay, let s be equal to a plus b plus c all over 2. Then, we can have this expression, equation. So a squared is equal to quantity s minus b times the quantity of s minus a times s times the quantity of s minus c. And then let's just rearrange this. We'll have this. And then square both sides. And we'll obtain this value. Since we are after with the area, it's positive. Okay, let's have the positive root. So now, for the formula of the herons, we have here the square root of s times the quantity of s minus a times the quantity of s minus b times the quantity of s minus c, where s is a plus b plus c all over 2, or known as the semi-perimeter of the triangle. Now, let's have an example problem. A businessman wishes to buy a triangular lot in a busy downtown location. The lot frontages on the three adjacent streets are 120 feet, 280 feet, and 315 feet. Okay, I think it should be 125 feet. Okay, 125 feet, 280 feet, and 315 feet. Okay, correction. It should be 125 feet. So let's have an illustration. So let's have this. Okay, we have here 125 feet for one street, 280 feet for another, and then 315 to another one. Okay, so given this, we need to identify the area of the lot. So in order to identify the area of the lot, we'll have the Heron's formula. So first, let's identify the semi-perimeter. So let's just add this 125 plus 280 plus 315 all over 2, and the result of that is 360. Okay, and then if we will apply it to the Heron's formula, we'll have the square root of 360 times the quantity of 360 minus 125 times the quantity of 316 minus 280 times the quantity of 360 minus 315. And if you will use your calculator, you'll obtain the area of 17,451.65 square feet. Okay, let's have this another problem. Three circles with the radii 3, 5, and 9 are externally tangent. What is the area of the triangle formed by joining their centers? So first off, let's try to illustrate this. Given that we have three circles here that are externally tangent with a radius of 3, 5, 9. So let's say we have here the smallest circle with radius 3. And then for the next one with a radius of 5. And then the last one, the largest among the three, with the radius of 9. Okay, so as you can see here, there's a triangle formed uh, by using the radius, okay, of the circles. So let's say this is triangle ABC. Okay, so from this, we can identify the sides. Okay, we can identify the sides. So here we have, again, we need to use the semi-perimeter. So here, this side is 5 plus 3 is 8. So this side is 8. And then this side, 3 plus 9, that's 12. So this side is 12. And then 5 plus 9 is 14. So this side is 14. So if we will apply that, we will use that. We'll have 8 plus 12 plus 14 divided by 2. The semi-perimeter here is 17. Then applying the Heron's formula, we have here the square root of s times the quantity of s minus a times the quantity of s minus b times the quantity of s minus c. Okay, so given that we have the semi-perimeter and the three sides, we'll have this. The square root of 17 times the quantity of 17 minus 8 times the quantity of 17 minus 12 times the quantity of 17 minus 14. So if you will use your calculator, you'll identify the area. Okay, so this one, okay, the shaded region here. If you will shade this part, okay, we need to identify this. So if you will use your calculator, the result of that is 47.91 square centimeters.